Okay, so this is the example for case 1, and this one would be b all over d, and again you can just find this directly. I mean, the value of this, you can find this directly. Section property, compact section. So you don't have to solve them anymore. Okay, so for this one, case 9, this is h all over the thickness of the web. And of course, the illustration would be something like this. Sorry, not that one. This would be the thickness and this height. Okay, and the limiting value is 3.76 square root of e all over fy. This one is 5.7 square root of e all over fy. Okay, so this is description of elements. And here you'll also find that it is unstiffened elements. And this one is stiffened element. Okay, so just to recall, we discussed the plastic moment capacity, or the plastic hinge phenomenon, I mean. So, the plastic hinge phenomenon, and also the unbraced length, and now the limiting width to thickness ratios. Okay, so now let's go on to the derivations and code provisions. Okay, so first we'll start off with these limit states for flexural member. Okay, so meaning how can a flexural member fail? Number one, it can fail by yielding. Okay, and that's going to be the plastic hinge phenomenon. Another one, it can fail by the lateral torsional buckling. And number three, it can also fail by local buckling. And this is this limiting width to width to thickness ratio. And number four, it can also fail by shear yielding. We haven't discussed this yet. This one, the last one, would be excessive elastic deflection. Okay, so for yielding, we have this beam and it's under flexural load. And at some point here, that all the fibers reaches the yield point, and therefore it's gonna collapse. It's going to collapse, referred to as the plastic hinge phenomenon. This one is if you have insufficient braced length, then it can't twist. And this one, local buckling, refers to the buckling of the elements. It is possible that you can have something like this. So, buckling of the web. And then this one fails by shear. Okay, so as the name implies, that's shear. It's yielding, but it is caused by shear. This one is yielding, but caused by bending moments. Then this one, deflection, is just simply deflection. So if you have deflection here, if it's too much, then there's going to be a limit state as well. Okay, so now let's talk about the nominal strength. So how to find the nominal strength of the flexural member, but again, we'll just limit our discussion to sections with compact flange and compact web. So let's write nominal strength. Take note of doubly symmetric compact I-shape members and channels. We bend about their major axis. Okay, so we will limit our discussion to this doubly symmetric. Okay, so take note that's doubly symmetric compact I-shaped members and channels and bent about their major axis. So if there's any problem or situations that does not meet this criteria, then it means that you cannot use the equations right here. Okay, so there's actually a table in the code wherein it also tabulates the limit states depending on your cross sections. It's something like a pictorial representation of this of these statements. Cross section. It says here you have an I shape and a channel, and if it's bent about their major axis, that's going to be this one. And if you have a flange slenderness, this one is web slenderness, and if the flange is compact, it says here compact, and the slender is compact, then the limit states would just be the flexural buckling. Oh, sorry, that's not flexural buckling. This should be yielding and lateral torsional buckling. Okay, so meaning that we are going to compute the equations. I mean, there's going to be an equation for yielding, and there's going to be a capacity or equation for solving the nominal strength or capacity in terms of the lateral torsional buckling. Okay, and if you read in our lecture handouts, it says that the nominal flexural strength, Mn, shall be the lower value obtained according to yielding and lateral torsional buckling. So whichever is or whichever gives the lower value, then that one will be preferred. Okay, so for yielding, our equation is Mn is equal to the plastic moment capacity. Okay, so take note, this plastic moment capacity is equal to Fy times dZx. Okay, so this is the equation, and this one is just simply the yield strength, and this one is the moment capacity. Then this Z sub x, this is just the section modulus, but it's in the plastic region. So plastic, I think that's the plastic modulus. Okay, plastic modulus along the x. Okay, so you can find this in the table. See table. Okay, so if it's just yielding, then you just apply this equation. Now for lateral torsional buckling, our equation depends upon the unbraced length. So we have to check if our unbraced length is less than L sub B, then LTB does not apply. So meaning that we don't have to worry with this lateral with this lateral torsional buckling. So LTB does not apply. But if our unbraced length is within L sub P and L sub R, then our equation is M sub N is equal to CB. Then we have this lengthy equation minus MP minus MR. But I guess the value here is just, you can just substitute this LR minus LP, but provided that it is less than or equal to the capacity, this plastic moment capacity. Okay, so the last condition is if you have an unbraced length greater than L sub R, then meaning that you have this equation FCR times SX as the section modulus, provided that it is less than the plastic moment capacity. Okay, so what is this FCR? This is the critical buckling stress, but this is different from the ones that we used in the compression members. Okay, so to solve that, we have FCR is equal to C sub B, pi squared E all over the unbraced length divided by this value R sub ds. Okay, wherein this one can be computed as 12. I guess I have already introduced you to this equation. Okay, so this is the equation for the critical buckling stress, and you would notice also that we have this parameter C sub B. This C sub B is referred to as the moment gradient factor, and actually just accounts to the uniformity of loading. So for us here, we'll just assume that C sub B is just equal to 1.0. Okay, so we don't have to worry for the value of this. Just assume that it is just 1.0. Okay, so now let's convert this condition in the graph. So again, this is our sorry, I think this one should be something like this. We have this earlier capacity, right? That's the capacity for the lateral torsional buckling, and here we have unbraced length and then nominal capacity. But here we have a limiting value, and that's going to be the plastic moment capacity. Okay, so at this point, this is our L sub B. The equation is 0.38 square root of E all over Fy. I guess that's our I guess this is not it. This is 1.76 or 1 square root of E all over Fy. And then this one, our L sub R. Our L sub R is this this one is LR is pi or ds square root of E all over 0.7 Fy. Okay, so our M sub R you'd also notice that we have this M sub R right here, right? M sub R. Now this M sub R is at this point. M sub R, which is just equal to 0.7 Fy Sx. Okay, and then I guess that's what we only need. Okay, so again, we're only considering doubly symmetric, compact eye-shaped members and channels spread about their major axes. So if that's the case, then the nominal strength will be based on the yielding and lateral torsional buckling. So for yielding, the equation would be simply the plastic moment capacity. It's just Fy times the section modulus. Okay, and the lateral torsional buckling depends upon the three conditions of your unbraced length. So whichever condition you are into, then you just have to check the equation for the nominal moment capacity. And finally, the design flexural strength is just equal to phi mn is the factor. The factory capacity is just simply this phi value is equal to 0.9. Okay, so the bending, the reduction factor for bending is just 0.9. Okay, so I guess that's the end of our discussion, and in the next video we'll do a sample problem for this flexural member. Okay, see you in the next video.